to this security testing and continuous vulnerability assessment track of cyber science. The second presenter of this session is Daniel Krohmer from the German Research Center for Artificial Intelligence. And he's presenting us a paper titled Decentralized Identifier Distribution for Moving Target Defense and Beyond. So welcome, Daniel. As for the previous speaker, you have 20 minutes more or less for presentation. So you should be able to control the slides from your laptop there. So over to you.
Thank you very much. Hello, everyone. My name is Daniel Krohmer. I'm from German Research Center for Artificial Intelligence, and today I will talk to you about decentralized identifier distribution for moving target defense and beyond. And yeah, the algorithms in this work are designed for network-based moving target defense purposes, which is frequently described as a continuous lateral movement of attack surfaces. For example, this movement can be achieved by performing identity manipulation within networks. And the general objective of MTD techniques of this kind is the impeding of hostile reconnaissance, the very first phase in typical kill chain models. Typical use cases include dynamic networks, platforms, dynamic runtime environments, etc., with memory ASLR being the most prominent representative for moving target defense. For decentralized IP-based host mutation, as we already introduced in previous works, it is likely to also have a decentralized identifier distribution. The reason for this lies in the key role of the identifier when performing moving target defense iterations, since it's responsible for guaranteeing consistent and unique addressing when IP addresses mutate over time. On the right side, you can see the mutation scheme of the moving target defense algorithm we introduced in previous works. First, we generate a message by concatenating the current timestamp with a unique identifier. Then the second step, this message is hashed by XORing a pre-shared padded key with a message according to the HMAC function. And in the third step, a modular operation is performed on the result of step 2 to adapt the actual IP range. The procedure is somehow related to the HMAC-based one-time password algorithm, also known as HOTP. But to successfully perform an extensive network operation of this kind, we need to define multiple requirements. The first one is that we need synchronized timestamps throughout the network. The second thing we assumed was a common pre-shared key. And there's a third requirement, which is mainly part of this work here, is the unique and consistent generation of identifiers. This slide shows the one step of a moving target defense iteration according to IP-based host mutation. On the left side, we first consider an attacker to be in the reconnaissance phase of an internal network after gaining access. The attacker already identified a target system A of 3 systems A, B, C, with the last IP octet .60, which runs, for example, a vulnerable telnet service. And at a predefined time period, all moving target defense involved entities perform a host mutation, meaning that they change their IP address without affecting the general functionality of the network communication. So as a result, the reconnaissance phase of the attacker becomes idle since he targets the telnet service of a completely different system, which most probably does not even run telnet. That's the core concept of the IP-based moving target defense implementation. So now, next slide. Oh yeah, okay. I think I skipped one, sorry. Yeah, okay. So for the identifier, we distinguish between self and lateral identifier. The self-identifier is the identifier which is actually generated and used by some network entity E index Y. And the lateral identifier, however, is the identifier value that every other entity yields to address the entity E index Y. With this, we constructed two conditions for an optimal identifier distribution, the condition for consistency and the condition for uniqueness. The consistency condition is the union of all lateral identifiers of E index Y, which must be equal to the self-identifier of E index Y. This basically means that a self-identifier and its corresponding lateral identifiers must be identical. Our uniqueness condition requires the intersection of all self-identifiers to be equal to the empty set. This obviously means that any self-identifier must not appear more than one time within the whole identity set. When both consistency and uniqueness conditions are met, we call the identifier distribution optimal and non-optimal else. On this slide, we see the relationship between self and lateral identifier. The diagonal values represent all self-identifiers of the respective entities, and the horizontal values represent the lateral identifiers of each related entity. For example, if the identifier theta index 1, 0 is the lateral identifier of the self-identifier theta index 0, 0, the very first here in the first line. The same applies for lateral identifier theta index I, 0, the next one, and so on. This means for an optimal identifier distribution, all entity sets E index 0 to E index n-1 must be identical after performing identifier distribution. The following algorithm flowchart shows the implementation of the identifier distribution algorithm we implemented. Here, system A generates both a token and an identifier. In our implementation, the identifier consisted of a 128-bit timestamp value and a 64-bit random number. Then token and identifier are concatenated and encrypted and sent to system B. And the encryption was performed with AES 256 algorithm, sorry. Subsequently, system B splits up the message after decryption into a token and an identifier. And the identifier is stored now as lateral identifier, and the token is reused for itself concatenating the identifier of system B. And this one is again encrypted and sent back to system A. And on the right side, we continued the flowchart. And system A again receives and decrypts the message, checks if the token is still identical, and then stores the identifier retrieved from system B as a lateral identifier. So for evaluating our implementation, we use an experimental setup with 40 virtual machine instances, and each experiment was conducted 100 times. We performed distributions in a sequential mode with different host numbers A to C, meaning that each distribution was performed one after another. And in addition, we performed distributions in the synchronized mode with different host numbers D to F. And the performance criteria was measured throughout the experiments. It was mainly the uniqueness, the consistency, the difference in sequential and synchronized mode, the timing behavior, and the overall network security objectives. And as we can see in the table, the optimal distribution rate decreases with increases amount of entities, with the sequential mode results performing better than the synchronized ones. We will discuss this in the next slides, but one reason for this might be the more extensive network load while distributing in the synchronized mode, which is way heavier than in the sequential mode. To analyze the uniqueness condition, we investigated the effects on the collision probability with varying numbers of network entities and possible identifier values. The evaluation was performed based on a modification of the infamous birthday problem. Here, the goal was to find a number of hosts and identifiers for the collision probability to become minimal. As we can see, collision probability decreases rapidly in the graph for increasing hosts and becomes near zero actually for a 128 timestamp and a 64-bit random number, which was used in our implementation, as said earlier in the slides. So in this case, consequently, we were not able to measure any collision for throughout all experiments from experiment A to F. In the next step, we analyzed the rate of consistent distributions throughout the sequential mode. On the left side of each on the left graph on the left side, on the right graph of the left side for synchronized mode. And as we can see, more errors occurred for a higher amount of hosts in general, and again, even more for those distributions performed in synchronized mode. We assume the significantly higher network load during distribution being the reason for this. And then again, we observed the packet round trip times for identifier distributions in different operation modes. In sequential mode, we found that the RTTs increased nearly linear, while in synchronized mode, anomalies could be observed for a high amount of hosts within the network. Again, we assume that that the high network load being responsible for this behavior. So in this work, we did research on the decentralized identifier distribution for moving target defense, which might also be applicable for other use cases in networking setups. We developed and evaluated specific distribution concerning uniqueness, consistency, and timing for sequential and synchronized modes. And future work will include the introduction of authentication schemes and integrity checks to improve the optimal identifier distribution rate, then DOS hardening, and the overall optimization of the round trip times, especially for synchronized distribution mode. So that's basically it from my side. If you have any questions, feel free to ask them. And else, I would like to thank you.
It's great. Thanks, Daniel. I think, yeah, so there is a question here. In terms of real-world applications, how can legitimate outsiders connect to inner nodes running FTP, HTTP servers when moving target defense in place?
Could you repeat the question, please?
Yeah, of course. So in real-world application, how can legitimate outsiders connect to inner nodes running FTP or HTTP servers when moving target defense is in place?
Yeah, that's actually a good question, and it's also a big problem of moving target defense, since in the experiments of that we conducted, the connection is always interrupted when performing an iteration of moving target defense. So there are some approaches to avoid this. There is a framework called CRIU. It's C-R-I-U, which tries to deal with that obvious problem. This framework tries to store existing connections and restore them after IP address mutation was performed. But after all, for now, we need to reconnect the existing connections while performing moving target defense operations. So yeah, this question is kind of unsolved right now. the issue is kind of unsolved right now.
Okay, thanks. I don't see any other questions coming through. So thanks, Daniel, for your presentation. And
Yep.
we'll be back at 1:30 UK time, so in 15 minutes for our third paper of this session. Thanks.
Thank you.